Good afternoon to everyone. This is Dr. B. Polaiah, working as a professor in the Department of IT, Institute of Aeronautical Engineering, Hyderabad. I'm very happy to give today our video lecture on the importance of Fourier transform and frequency domain. This is the topic which we wanted to concentrate as important of Fourier transform and frequency domain, which the concept will be helpful us towards to understand the image processing. That is the part of image processing syllabus. We are going to be understand the major topic as we call as Fourier transform and frequency domain. So this Fourier transform and frequency domain is the one of the domain which we are going to be used to understand in the better image processing, where we apply such a transformation techniques, such a transformation method, such a transformation mathematical models. Okay, so why we want to concentrate such a transformation? So better image processing take into an account long range correlation in space, conceptual insights in spatial frequency information, that is, it means to be smooth, moderate change, fast change, and also we concentration on fast computation, which we are going to be concentrate in of the differences or which we are going to be concentrate as a distinguish in between convolution versus multiplication of the image processing. Such a image representation which we can connect it from one image to the another image for the sake of detailed study. For example, the image which we are concentrating here is an image which we want to identify either any tumor or any instance of information as per medical representation is attained in these images. That is, these MRI images are also needed such image processing in terms of smooth and moderate changes towards to get fast changes of image processing information, which we call as fast computation by the help of convolution versus multiplication. So let us we go in detail about this image processing, which we want to understand in terms of alternative representation and sensing. So the transformation which we are applying here in terms of data as a measurement in the radiology images, or the data which we are going to be collect or acquire from medical field, and also we concentrate on astrophysics. So these are the fields which help us to understand the image transformation for the measurement in terms of radiologists. Or also we are going to be concentrating inverse transformation to recover image. The efficient storage and transmission, which we want to understand energy compaction, that is pick a view representative basis. For example, just store and send a contribution from one basis to the other, which we are going to be collect one figure for image transformation from one to other. So this you wanted to calculate this information which we want to understand part by part or sequentially part. So we are going to be understand that based on your frequency domain applied information. So here how we can apply that transformation based on the different aspects of image transformations. Number one, orthogonal sinusoidal basis function, and number two, non-sinusoidal orthogonal basis function. Number three, the basis function depending on statistics of input signal as well as directional transformation. If we go in detail about each one separately, respective of this image transformation, which we want to concentrate not only Fourier transformation but also discrete cosine transformation, discrete sine transformation as well. So if suppose non-sinusoidal orthogonal basis function which we apply as a transformation technique, as a transformation method is Hart transformation, Walsh transformation, Hadmord transformation and slant transformation. So here also we are going to concentrate on some other which we call based on the basis function depending on the statistics of input signal, that is KL transformation, singular value decompositions. So and last, this image transformation, we also concentrated on directional transformation, number one, off transformation, random transformation, Ridgely transformation, counterlap transformation, which here random transformation also very important. So coming to the transformation is what? What do you mean this? How can you define transformation? It is a signal can be converted from time domain into frequency domain using mathematical operators called transformation. There are many kind of transformation that does not this information process. Some of them are given below as Fourier series, Fourier transformation, Laplace transformation, and Z transformation is also very important. Z transform which we are calculating in both as a discrete applied. So Laplace transform will apply in continuation, but Z transform will calculate in discrete only. In discrete it is continuous of frequency signal. So coming to the what is that type of signal which we called as a continuous or discrete in the sense? Let you take that signal which we call as a cosine signal wave in terms of frequency. It is a time domain. It is in the time domain. It is in the frequency domain. It is in the frequency domain. That is what we are representing here. Okay, so when we are sinc function used, but in the frequency domain, we use the uniform band of frequencies, which is pulse. And where Gaussian we apply, here also Gaussian will be as it is, and double exponential will be called as Lagrangian frequency domain transformation we are using. So coming to the such a transformation which we are applying in terms of sound wave or the sound which we are calculating in terms of minimum to maximum. 3000 to 5000 hertz of the frequency signal which we are transforming into the certain volume that we are keeping into the frequency instead of frequency domain as a time domain signal with respect to sound volume, then the wave will be vary in terms of just like a random wave. And where we are going to see the same in the frequency domain, that 3000 hertz to 5000 hertz, how it will be varying, we can see in the spectrum strength, in terms of spectrum strength. So, which we can understandable how this importance of Fourier transform in terms of frequency domain from the how this Fourier transform will be help us to convert a time domain signal into frequency domain signal. Okay, so then we also understand that another important point is here the visibility of the signal information and its quantity of value also represent in easy manner by the help of frequency domain. So that is the what we can find out the difference in between what we call time domain and frequency. So and also we understand here we extendedly concentrate not only just transformation process but keeping on the Fourier series. The Fourier series is simply we called as so Fourier series. Also we are concentrating here. The Fourier series simply states that periodical signal can be represented into sum of sines, cosines when multiplied with a certain weight. It may be called as a Fourier series. See, in further states that periodical signals that can be broken into a further signal with the following properties. The signals are sine waves or cosines which are have some harmonics of each other. So, once you understand Fourier series, let me compare with Fourier transform. The Fourier transform simply states that the non-periodical signal whose area under the curve is finite can also be represented into integrals of the sines and the cosines after being multiplied by certain weight. So the Fourier transform has many wide applications that include image compression, image filtering, image analysis, And if the images are non-periodic, the Fourier transform is used to convert them into the frequency domain. That is the major importance of Fourier transform by comparing with the Fourier series. So this Fourier transform is also concentrating on as an important image processing tool which is used to decompose an image into its sine or cosine components. So the Fourier transform is used in a wide range of applications such as image analysis, image filtering, image reconstruction and image compression, where this Fourier series and Fourier transform to convert a signal into frequency domain. Both will do the major job on conversion time domain to frequency domain. So also concentrate that difference between the spatial domain and frequency domain. In spatial domain, we deal with images as it is. The value of the pixels of the image changes with respect to scene, whereas in the frequency domain, we deal with the rate at which the pixels values in the changing as it is in the spatial domain. So we understand that so far about Fourier transform and its Fourier series differences in respect of frequency domain. But such a domain we also applied in the form of filters. That means if you want to define the filter, the concept of filter is in the frequency domain is same as the concept of a mask in convolution. So after converting an image into image frequency domain, some filters are applied in filtering process to perform different kind of processing on an image. The processing include blurring an image, sharpening an images, etc. So the common type of filters for these purposes are ideal high pass filter, ideal low pass filter, Gaussian high pass filter and Gaussian low pass filter, which we are connected in terms of different common type of filters for the purpose of frequency domain, which we are going to be concentrate on different kind of processing on an image processing. So coming to the such a examples which we want to concentrate by the help of frequency components. So we have to understand about frequency components also. So the meaning of frequency components is here, any image in spatial domain can be represented in a frequency domain, but what to do these frequencies actually mean? We will divide frequency components into two major components. High frequency components are used in terms of corresponding to edges in the images. Low frequency components are in the image corresponding to the smooth regions. So that is the major difference between high frequency components and lower frequency components. So such a difference we can also concentrate by the represent certain signal representation is as is in the above. Last signal is actually the sum of all the above signal. This was idea for to understand Fourier transformation to connect all these signals to get your required signal. So how it will be calculated? How it is calculated? Since as we have seen in the frequency domain that in order to process an image in frequency domain, we need to first convert it using a frequency domain, and we have to take inverse of output to convert again back into the spatial domain. Then we will arrive by the both Fourier series and Fourier transforms of two formulas are useful here. In one of conversion and one converting back to the signal spatial domain. So once you understand such a conversion by the use of Fourier series and Fourier transform, but those how it is internally processed by the help of certain mathematical principles which follows some properties of the Fourier transform, those properties of Fourier transforms which are listed here. Number 1, separability. Number 2, translation. Number 3, rotation. Number 4, periodicity and complex conjugate. That is 4th one. And 5th one is rotation. And 6th one is what we call as distributivity property. And 7th one is scaling. and the eighth one is convolution. These are the properties of Fourier transform which we are applying in terms of mathematical model of formalities for converting time domain signal into frequency domain, which we are concentrating in terms of spatial domain. So let us we see the first one which we want to understand in terms of what we called mathematical way, separable property. The Fourier transform of separability of the frequency for the image object function of f of xy, keeping into the frequency domain as capital F of u comma v, where we use this f of x comma y from the 2D transformation divided into 1D transformation. The translation property which we are applying here, frequency transformation of f of x comma y is equal to f of u comma v. That is the frequency transformation. So let us we understand one more properties of frequency transformation, that is periodicity and complex conjugate. The frequency transformation of f of x comma y is f of u comma v, where f of u comma v is applied in terms of f of u plus n and v plus n, keeping into the f of u plus 2n and v plus 2n, etc. So where this scaling factor is applied here in terms of your selected object function is real, and then the applied Fourier transformation also exhibited in terms of complex conjugative value. So to understand the symmetry of the properties of periodicity and complex conjugate, we can also define in terms of mathematical way f of u comma v of this f star will be here, f star of u of minus u comma minus v. So that is the magnitude of f of u comma u will apply here your frequency information. It is correct only. It is correct. So that is what we have to understand as a property. It's a property. We cannot change any even simple factors of values or multiplications. Okay. So as it is, we have to understand and apply to the your frequency transformation in its domain. So we'll see the next one, that is rotation, where we apply the frequency transformation of object function of an image, which transform f of x comma y equal to f of u comma v, where x is the and y are vary with respect to r and theta. So what do you mean this r is replaced the x and y will be replaced from theta value, which is changing even with the initial condition value of theta naught. These are initial condition values which we applied for the understanding of rotation process. And coming to the another property of your frequency domain, which we concentrating on distributive property. The meaning of distributive property is very simple to understand. We are expanding f1 of x comma y is plus f2 of x comma y, where we are going to be get f of f1 of x comma y plus f of f2 of x comma y, which we are going to be simply understand your transformation from one to other. But where is it equal? But it is does not equal, because here we are using the separated product values. In addition is same, but product wise is not equal. Next, coming to the we want to extend for understanding about the spatial domain to the frequency domain, where we keeping on a digital image is convert from spatial domain to frequency domain is also important. In the frequency domain, the importance of process is here. Image filtering is used for image enhancement for a specific application. That is, we are going to be used such a specific application is here. I want to mention that in terms of restoration, image restoration process. A fast Fourier transformation is also a tool of the frequency domain used to convert spatial domain to frequency domain. So where your spatial domain is concentrating towards the representation of a signal allows you to observe in terms of several characteristics of the same signal that are either not easy to see or not visible at all the when your signal look at signal in the time domain. So you can also concentrating here, for instance, frequency domain analysis becomes useful when you are looking for cyclic behavior of a signal. So let us we see the theory which we are discussing here may be some little bit confused, but here we represent the same process by the help of a simple block diagram representation, which we can understand here by taking any input image, apply the frequency domain, that is frequency distribution, that is depends upon the properties of frequency, and we process the pre-processing, then we will apply the inverse transform, then we will get your required output image. So what do you mean to happen here? If you want to reduce some blurred process, you can do in this frequency transformation towards to frequency domain. So for example, let you see here for the sake of frequency domain, this is spatial domain, okay, and convert into frequency domain, which we want to keep in certain communication channel, which we want to send instead of spatial domain of the image signal to frequency domain signal. It is applicable by the help of Fourier transform only. So we can extend that process by the help of another simple diagram representation by the understanding pre-processing and post-processing. Here the difference is here Fourier transform is completely depends upon pre-processing, which we are connecting input image and getting output image. In terms of your one of the application we call enhancement image processing, also we call as restoration process of image. See here apply the Fourier transform is here by the help of properties of Fourier transform, and we apply the filter the function which we are listed filters based on your selecting you can apply, and apply the inverse Fourier transform, then you will get the your post pre-processing towards to get from g of x y. That is simply you can say f of x comma y is converting into g of x comma y. How? What is the meaning of conversion is here enhancement. What is the use of this enhancement of the image is helping us towards restoration process application. So we also extend to understand not only in terms of specific domain, but if we want to concentrate as in terms of two-dimensional Fourier transform can be generalized to higher dimensions. For example, many signals are functions of 2D spaces defined over an x to y plane. In two-dimensional Fourier transform also has 4 different forms of depending on whether the 2D signal is periodic or discrete. So that periodic means continuation domain. So discrete means instance of the domain process, which we are going to keep in terms of discrete domain. For the application of here, we apply the fast Fourier transform, which we call FFT, is an algorithm towards to compute the discrete Fourier transform of a sequence, or it's a DFT. Okay, DFT in terms of inverse DFT. So later we can take one of the example which we called so far some mathematical domain of Fourier transform and its domain. So let us we say for example separable functions can be written as f of x comma y separate into f of x comma g. It is f of x into g of y. So where this Fourier transform separable function product of ft, that is ft means Fourier transform as two functions. By the help of these two functions, we convert into your required form by the spatial domain process dx dy. It is continuation domain, it is not discrete. So when we applied this, we expanded your complete integral formula based on properties of Fourier transformation, and we'll get finally your convolution of the Fourier. So with this, we also extend this concept which you understood so far, the importance of Fourier transform and Fourier series, and which we are in terms of spatial domain to frequency domain. Also, you can refer some more textbooks, number 1 and number 2. So with this, I want to conclude that Fourier transform and its frequency domain is a more important towards to convert an image into your required image formation by removing the unwanted signals. Okay, I'm very thankful for your understanding about this importance of Fourier transform and its frequency domain. Thank you so much. We'll continue the same concepts with additional information and as per our syllabus. Thank you so much. Thank you.
Like, share and subscribe. hit the bell icon for more updates.